Okay, so this is a continuation of the lecture I did a while ago at my house because the bus came. Uh, so yeah, last time, or at least just a while ago, um, we talked about the disk and its relation to a circle or a one-dimensional sphere. Not really one-dimensional hypersphere. So yeah, and I already defined or show you guys what a ball is. So we have a closed ball, which is this equals r squared, x, y, z. R exists in a four-dimensional spacetime, or at least we have a four-dimensional output, and then we get a third-dimensional object or surface. Not really surface, but object. So this is the open ball is just its interior, or the interior of B3. Oh no, sorry, it's not equal. Less than or equal. So we just remove that equality sign. Plus z. Less than r squared. So it's strictly less than. It can never be r. X, y, z, r in R4. So this is the closed ball, including the boundary. The boundary is precisely S2. Now that's the crucial relation I want to point out between the ball and the sphere. Not that they are the same or they have an exact equivalence relation, but rather one is, or the latter is the boundary of the former. Like how the sphere or S1 is precisely the boundary of the disk D2. Okay. So now we can think of this as a map from R4 to R3. So it maps R4 onto R3. And this doesn't necessarily mean that the space that we're mapping from is four-dimensional. It's just that we have four inputs, and yeah, we have a three-dimensional output. And specifically, the points x, y, z, and r, not n, are taken to the relation x squared plus y squared equals x squared plus y squared plus z squared equals r squared under this this map. So yeah, this is what it is. So this is the ball. Now the interior of B3 has no boundary by the definition of an interior, or the interior of a topological space. So the boundary of the interior of B3 DN. And this crucial relation, the boundary of the ball, closed ball, is precisely, or not really precisely, but homeomorphic to, it's homeomorphic to S2. Okay. So now, to femboize it, what we just have to do is say that these four are part of a four-dimensional femboid or four-dimensional fundamental femboid space. So just say to femboize it, we just say that all of these exist in F4, and B3 maps F4 onto our F3. Okay. and then this is F, FB3, FB3, FB3. So the interior, or the boundary of the interior of FB3 doesn't exist. Well, the boundary of the closed one, FB3, is precisely FS2. Okay. So now we're taking four femboids, and by our usual notion of, or our intuitive notion of exponentiation and sum, we say that they strictly satisfy this relation or this relation. And as I stated in the previous lecture before this one, or the previous footnote, the structure is carried on over because there is an exact isomorphism, well, not really exact, but there is at least an isomorphism between the space of all femboids and R. Now you may be thinking, well, it's not precisely an isomorphism because it is an injection, because R is intrinsically, or could be intrinsically, bigger than F. And I mentioned that in foundations, I think, or in another footnote for this course. But the thing is, that depends on how you define our fundamental space of all femboids. If we say that this is intrinsically isomorphic to the integers, we're saying that they have precisely the same exact cardinality. That the cardinality of the integers is precisely the cardinality of F. But we can define F to be somewhat the same, or we can say that every femboid, or the cardinality of this, can be the same as the cardinality of the real numbers. So it's all a matter of how you define your F here, whether it would precisely be bijection. If we define F to be strictly, to have a cardinality strictly greater than the cardinality of the integers, that means that it would be a surjection with respect to the integers. It would not be an isomorphism. But if we say that it is, it has an isomorphism with R, that means it is now, it's a bijection between R, but this time it would be a surjection with respect to the integers. But if we say it is isomorphic with respect to the integers, then it would be an injection into R, or an embedding, because the integers is a subset of R, and then we're mapping it onto, or saying that it is isomorphic to a subset of R, so it's somewhat like an embedding. So it's a matter of defining F here, and that's an important thing too. You need to specify what exactly F is in order to avoid some ambiguity when it comes to cardinalities and maps between them. So you have to pick one or the other. It cannot be a bijection for both the integers and the real numbers. Okay, so yeah, very important thing. So I'm gonna list it as a theorem, or a conjecture. No. I'll just write it as a theorem. Theorem. If F is isomorphic to Z, it is not isomorphic to R. And if F is isomorphic,
keep going.
Sit down.
Keep going.
Sit down. If F is isomorphic to R, it is not isomorphic to the integers. Now, proof of this theorem. Chad, will you please
The board is
sit down? Will you please sit down? You're covering the board.
Just standing here.
You're covering the board. Will you stop? Like,
Right.
no, I'm serious. Like, you keep doing this every lecture. You're wasting my time.
Cameo, man. Yeah.
You're wasting my fucking time. Okay, so proof of this theorem is that the cardinality of F is strictly not the same as the cardinality of Z if, and only if, F is isomorphic to R, and the cardinality of F is not the same as the cardinality of R if and only if F is if F is isomorphic to integers. I mean, I'm assuming that there is the group operations here is addition or multiplication. Okay. Okay. So the reason why the cardinalities would differ, or the reason why it wouldn't be quite the same, because for bijection to be a bijection, bijections must have, the sets that we map onto each other must have the same cardinality. For any sets A and B, gamma that maps A onto B is only a bijection if and only if the cardinality of A is equal to the cardinality of B. An isomorphism. Okay, I'll just write it in notation. A isomorphic to B is strictly an a bijection, not isomorphism. Okay, so let's assume that let's assume that F is isomorphic to Z. Then this would mean that it doesn't have the same cardinality as R. Because the integers is strictly smaller, or have a cardinality that is smaller than R. In terms of topology, we say that Z, or the integers, is strictly coarser than R. R is finer than Z, which means just bigger. So it's smaller. So this is smaller, this is bigger. Okay. So since it is not equal to R, so the cardinality is not equal, so therefore it is not a bijection. So there does not exist a bijection. Between A and B. Okay. So, and the next, assume that F is isomorphic to R. Assuming the necessary group operations that satisfy it for it to be a group. Okay. So therefore, the cardinality of F is strictly greater than Z, because it has roughly the same cardinality as R in order for it to be isomorphic and thus have a bijection. So there does not exist a bijection between sorry, this is F and this is R. This time it's F and Z. Unity. So an important thing you guys need to know is that isomorphisms are supposed to be, or they need to be bijections, because isomorphisms are it's an equivalence class essentially between the elements of one set and the elements of another set, according to So this must hold, or this really must hold for two sets in order for them to be bijective, or not really bijective, but isomorphic. So yeah, that's just so after we state that theorem. This is an important thing, theorem. I think we're going to apply it in algebraic theory. So, as that, So another thing that we want to ask ourselves is what happens if we take the Cartesian product between, we already asked that, we take the Cartesian product between Fs1 and itself, we get a femboid donut. Okay. But we neglected to ask what happens if we take the Cartesian product between Fs1 and V2. So,
Kasi sabi niya, announce daw nung rep. So yan ang in-announce. Oh my God, may sinagot akong school uniform. Sino yung nag-message sa akin? Woo! Ay, ay! Dun. Punta ka muna sa clinic. Okay na.
okay.
Clinic ka muna.
So, this here gives us a hollow torus, so it just gives us the shell of the torus. But the thing is, if we take the Cartesian product between a circle and a disk this time, we would have a solid torus. Because every point on that circle, or every point of the circle is correspondent, or we place a disk inside it, so it sweeps around, and it gives us like sort of the inside or the volume of it. So we can say that FD2, the boundary of Fs1 cross Fd2 is precisely Ft2. And you can say that Fs1 cross Fd2 is the interior of Ft2. Okay, now that we constructed a solid torus, what if we squash the torus onto two-dimensional space? So to speak, what exactly is T1? The T1 is not really a torus. Like if you look above, or if you look above from a torus, like a bird's eye view, instead you would see an annulus. Okay, you get an annulus. So T1, let's define T1 as an annulus. And the precise way to model this torus is via this equation. So T1 is, roughly speaking, x squared plus y squared minus r1 squared times x squared plus y squared minus r2 squared less than or equal to 0.
Present si Mika and Toby. Absent pa rin si Toby.
R1, R2, this in R4. So this is an annulus. It's just a sort of a one-dimensional version, strictly, or like a two-dimensional version of a torus in terms of geometry, at least. So T1, as you notice, like, it's a surface. It's definitely a surface, but it's still sort of. It sort of works the same way like a sphere. It's also a map from R4 onto R3. Such that it takes these 4 points and then it gives us this relation in R3. It's still in R3 after all. Or R2, sorry. So this sort of breaks our notion. Of mapping from n plus 2 space onto n plus 1 space. So this is the only case that breaks our notion in the last lecture about mapping from one space to another, using a shape, or envisioning a shape as a mapping from one space to another. So yeah, that's an annulus. To femboize it, all we have to do is just say that they're part of F4. Now this is a closed annulus, an open annulus, which would look like this. Would be this, but I just removed the equivalent, the equal sign. So it's just strictly less than 0. So yeah, and it's just the interior of this. Strictly less than 0. Okay, so that's annulus. So the boundary, so FT1, now we don't say it's precisely that, but FT1 is sort of, you can think as homeomorphic. I don't know that I'm aware that there must be a different definition for this, but we say that FT1 is homeomorphic, I would say, to, or you could say, to the boundary, or by definition, to the boundary of F CA. Actually, this is supposed to be for CA. Closed annulus. And then this is closed annulus. This is F open annulus. There. Now, yeah, I could go on about corresponding these things. We're gonna apply the theorem now. In the next footnote, we're gonna be applying a theorem and mapping or using some maps from a separate lecture or separate footnote to relate this with R. So that's a good place to stop.